Hello and welcome to the segment 3. In this week, segment 3 will completely go into the implementation for memory and throughput techniques for LLM training. So these are precisely designed for LLMs, and we will extend this session into the next two segments for completely fine tuning and adaptation. So in this segment, we will discuss completely the memory throughput. So talking about memory, obviously you need to understand the GPU memory anatomy. For that, we had very good discussion in the previous weeks. What exactly is the memory hierarchy and different sizes of VRAM that is available for different GPUs, and obviously they can be of different technologies, and based on that you have different bandwidth. Irrespective of whatever the size of the memory or the bandwidth that the system offers, how we can optimize the memory in the program itself from the PyTorch or the TensorFlow framework, that exactly we will see. In the previous session, we talked about the mixed precision, right? So we have talked about different precision data type that is available, and for the AI workloads, mostly for the transformer models and large language models, what kind of autocasting will give the impact in the performance that we have seen. In this session, we will go deeper details of automatic mixed precision, which uses FP16 for or FP16 tensor cores for the earlier generation GPUs and BF16 for the next generation or newer generation GPUs. So nonetheless, we will use the 16-bit precision for this automatic mixed precision training, and we will show the demonstrations in this segment in T4 GPU again, just for you to understand and freely run the codes for learning purposes, and obviously you can extend it for the other GPUs as well. Okay, so in this segment we will exactly see what is the impact of mixed precision, because we will not go deep details of discussing the mixed precision, we have already discussed that, and the impact of few other techniques like gradient checkpointing, which is to trade off the compute for memory. So here we are solely focusing on optimizing the memory and throughput. So you should not think about how to accelerate the compute part or compute element of the LLM in this segment, because here the sole focus will be on memory optimization, and in the next sessions we will also again come back to both combined memory and compute. So that way we will have the complete picture of the optimization and acceleration technologies for large language models. Okay, so here we will also see the impact of gradient accumulation. Gradient accumulation technique, what is exactly it, that we have seen also in the previous session, but again we will discuss with the impact in the batch size, how it impacts in the throughput and memory optimization. So here talking about the configuration for the GPU of T4, we have the 16 GB video RAM, and we have 320 GB per second memory bandwidth and 365 teraflops of floating point 16 tensor core, and we have 8.1 teraflops for the full precision FP32. Again, for the environment setup and the GPU memory availability, you can check with the same program for across the different GPUs that are available. But here let's look at the GPU memory that is acquired by the LLM. Precisely what are the components that is getting stored in the memory while we train the large language models. So here you go, you have the model weights. Model weights are the parameters. Then the gradients. Gradients are essentially the byproduct of your back propagation, right? So it has the same shape as weight. Okay, so you can see that we usually store full precision for the parameters gradients. So you have FP32, so 4 bytes per parameter, 4 bytes per parameter, and the optimizer states 8 bytes per parameter. So basically if you have different optimizer, based on different optimizer you store the states. Here we have the Adam optimizer where you have the first and second moment to store. So this is the Adam optimizer. Again, if you have weight decay along with it, you have another parameter along with that. So basically for 2 parameter optimizer we have 8 bytes per parameter. And activations depends on the batch size. Again, going to the basics, what is training? You have the forward pass, you have the loss computation, you have the backward pass. In the backward pass you compute the gradient of the loss function or loss value with respect to each of these parameters, and for that you need the outputs of each layer, right? Each layer, what exactly you are getting the output, that you have to store to compute this gradient. Okay, so that's the activations. So essentially you have the model weights to store, you have the gradients to store. So it's not only the model size, which is basically the parameter in terms of parameter, but plus you have the gradients and then the optimizer states as well as the activations to store. Now once you understand exactly what are the components that is going into the memory, then you will be able to optimize. Now you can optimize the gradients to reduce the memory. You can optimize obviously model weights, that also there are techniques. Optimizer states, you vary the optimizer, and activations, there are techniques like you have the gradient checkpointing. So again we'll look at the different optimization techniques in the memory, but now you understand what are the components that are stored in the memory, which is occupying the memory. So essentially in terms of size, floating point 32 plus Adam optimizer will take total of 16 bytes per parameter, right? So you can see total 16 bytes per parameter. So for a 7 billion parameter model, right, so the size is 7 billion into 16. So essentially effective size is 112 GB, which needs multiple A100 GPUs. Usually A100 GPUs have 48 GB memory. You need at least 3 such GPUs to completely accommodate all the states in the LLM training for this very simple model, which is 7 billion parameter model. These are very early stage large language models like Llama 7 billion and other models are there. However, if you go for full-fledged state-of-the-art models which stores trillions of parameters, and you can imagine how much such TBs or petabytes of data that you need to just store for training. Okay, so this is just one batch of training. Okay, so now you can do the profiling. I am not going into deep details of this code. This is just to have the idea about what is the baseline empty GPU size, and if I, let's say, store a model with 23.4 million parameters, I am allocating around 90.2 MB in the memory. So again, I mean, you can just go into the calculation which follows the same component calculation for memory size. Okay, so here we are using this small transformer block. This will be the basic building block for the language model that we will create. In the last class we had seen one causal language model. In this session we will build one language model based on transformer so that we can go through again the layers of the transformer model just for better understanding of the memory that is being used inside these blocks, which is the block unit block here, one transformer block. So what are the blocks here? So D model is the size of the multidimensional vector after the tokenization, and then it is spread across the 8 heads. So 8 heads of multi-head attention takes the 512 dimensional vector, and basically in the end you have the expansion of this vector input to your feed forward neural network expansion of 2048 neurons or the size. Okay, so this is your block, and where you have the self dot attention. So this is basically your multi-head attention, number of heads and batch first, and D model So this is the input dimension. You have the number of heads, and then the feed forward network 1, feed forward network 2, and then you have the normalization layers and dropout layers. So this is your block, and then we are doing the benchmarking model, which has the embedding, positional embedding, and then the blocks have been called, okay, number of times. So how many number of layers that we want, those many number of layers this transformer block will get iterated, or it will get stacked to make this entire network. Okay. So this embedding is basically doing the mapping of the vocabulary size, let's say how many unique number of tokens that we can map. So basically usually this vocabulary size in thousands, like GPT-2 uses a vocabulary size of 50,000, around 50,000. So those many unique tokens that you can map. And D model is the multidimensional vector of the tokenization. You have the positional embedding. So essentially we are taking the maximum sequence of 512, right? And then the inputs are given to the blocks. Okay. So this is your benchmark model, which uses the small transformer block as the basic block or the basic building block. Now the forward network is there. For the each block you have the X equal to block. Obviously now we can actually see the optimizer states, model weights, and forward pass with different dimensions. So for this, so essentially we have the model with 23.4 million parameters. So we usually allocate 90.2 MB with reserved memory size of 104 MB. Now theoretical weight size is 89.2 MB. So this is after model to device. This is after model to device. So when we run this model to device, so basically these weights are getting transferred to your GPU VRAM. After the optimizer creation, you increase the Adam state size, which is basically taking around 178.4 MB. Okay. So after the forward pass, this much of memory is allocated. So weights plus activations plus the optimizer state, and then when we do the backward pass, then the gradients will be calculated, okay, which will be around this size. So you can see the model size is around 90.2 MB, but the training phase, it is taking when we run the backward pass, it is allocating around 679.6 MB, which is around 7 to 8 times than the allocated memory of this raw model. Okay. And the theoretical gradient size is 89.2. So this gradient size will be stored along with some overhead. So if you see this total theoretical size for this particular model, which is basically the weights plus gradients plus the optimizer states, which takes around 356.7 MB, but actual GPU memory allocated will be around 765.0 MB. The difference is due to the activations, CUDA context plus the framework overhead, which framework you are working with, that will cache or that will have some extra overhead, which will take some additional memory. So now you know how the memory is getting impacted by the training with different factors, activations, optimizers, the gradients. Okay, so if you try to see the memory breakdown visualization, so if I have, let's say 7 billion model, which is 7 billion parameter model, so here is just the simple calculation that we have just followed through, and we just plot this. You can see that the baseline, which is AP32, is around 112 GB for this 7 billion model. Weights only with BF16 or AP16, 16-bit quantization. So with the reduced precision, you are taking around 98 GB, and then when you run with mixed precision, obviously not only the weights, so everything is accounted here in the mixed precision, you have the 70 GB of total memory allocated. And if I go for very aggressive 0.3 optimization or the precision reduction, which is available for very modern GPUs, which will take around 9 GB. Okay. And here you can see in this pie chart the training parameter, their percentage of occupation in the memory for that matter. So for this 7 billion parameter model, we have these gradients taking around 21%, weights around 23%, you have the optimizer around 21%. So activations will be either increasing or decreasing based on the batch size. If you have 4 batch size, 6 batch size, or 8, 16 or so on and so forth, based on that these percentage will get increased. And the optimizer, obviously now you have total optimizer size of 42%. Okay. So here you are seeing the example here with 700 million parameters. So total how this distribution of size or memory occupancy happens across the different states and different parameters and activations that we have seen. So we will discuss the QLoRa part in the upcoming sessions, but before that we will just see about the mix precision and the automatic mix precision, how it impacts the memory throughput. Okay. So usually for the tensor cores which run the FP16 matrix multiplications, which gets around 8 times throughput compared to your FP32. Okay. So AMP automatically casts eligible operations, as I discussed in the previous session, the multiplication, the convolutions which are eligible for your FP16 or tensor core operations. So tensor core which is capable to run the data with the FP16 computations. Okay. So those computations will be directly diverted to the tensor cores, and they will be mostly the operations like matrix multiplication, convolution and so on. And you have the sensitive operations, the layer normalization, the softmax computation, loss computation. So those happens in the full precision, and then the scaling of the loss function will happen if there is underflow in FP16, we have scaling, and unscaling will happen if we apply the scaling. We have to revert the scaling for the gradients. For that we have this unscaling. Okay. So these are the parts that we will see in this section to go deeper to understand how the impact happens in the code as well as the training of the complete language models. Okay. So for your reference, the FP16 range, which is very tiny, you can see it can take maximum of 65,504 value both in plus and minus range, whereas your 32 range you can see. Obviously BF16 will have the higher range. Okay. So here we will just try to see how the underflow and where exactly this underflow happens. The values smaller than this will go to 0, so that we discussed, and in this code you have seen that the gradient value which is going under this, as per your AP32 it will have preserved value which is correct, but AP16 will underflow. And if we do the scaling, let us say we scale with the factor of 65,536, the scaling will happen and this value will blow up, and that point of time if we cast, it will survive, the value will survive, and after unscaling the value will get the original value recovered. So essentially this scaling, unscaling and the casting, these three are interrelated operations that happens in the AMP library. Okay. So here are the operations which are eligible for your AP16 cast, and here are the operations which are safer in the full precision. Okay. Obviously, I mean you can cast it to the few of the operations you can cast, like normalizations also you can cast, but obviously you will get very poor performance for that matter. Okay, so let us see one full training with the benchmark model that we have had. Okay. So now we can see the vocabulary size here for this particular language model is 8192, the tokenized vector is of size 512, total of 8 head in the multi-head attention is there. The feed forward network has 2048 expansion of the 512 dimension input, and we have 6 layers here and total number of classes, that is the output of the final logits, which is basically 10 here, and this entire model I am transferring it to the device. Okay. So now the data loader part, that is fine, this I will not go deep details because you have already seen so many data loaders. In the training epoch, That means when we call this training epoch, we want to train the model for one epoch, which will return the average loss value, the time, and then the peak memory in MB that is acquired. Okay, so here this most important part that we want to see is the scaler, because the gradient scaler, which preserves the value automatically by scaling, downscaling, upscaling, downscaling the values, and try to adjust where exactly it should apply, where exactly it should not be applied. Okay. So try to see here or concentrate here bit more here, because here we are creating this use scaler, which uses obviously float 16 if I have the CUDA available. So that way I create this scalar object, which is basically your torch.amp grad scalar, which will either enable or disable. For this case we are using the CUDA, so it will be enabled, and then the performance counters are enabled to just measure the timing. Okay, now here for each batch, for each step, I will come into this step and batch in the later phase. So just try to concentrate on the context here. So here we are creating the AMP context, which will create the autocast. So essentially with torch.amp.autocast, this autocast use we have seen before also, and here we are using with the enablement of the use AMP, and also we are using the float 16 in this case. Okay. So now the logics are basically the outputs of the model, and then the loss is applied or loss is calculated by the criterion here. Okay, so now if we are using scalar, which is this grad scalar, okay, so here we do or we apply the scaling of, I mean the loss value, which is this scalar dot scale loss. So it will scale the loss up before starting the backward. So that means before computing the gradient. So if my loss values are very low, which has already been casted, okay, so that means I do not have the gradient. So essentially it will get 0. So to make or to keep the gradients alive while we are doing the backward pass, we need to scale this loss, and after then we apply the backward, which is the gradient calculation. After the gradient calculation we unscale, because we need to get back the value without scaling. So unscale before manipulation of the gradients. So we compute the loss, we apply the scale, we do the backward, then we do the unscaling before the gradient manipulation. And here we are doing another one gradient manipulation, which is keeping the gradient values within the range of 1, just to make sure that your weight updates do not get too much. Okay. And then we apply the scalar dot step. It is similar to optimizer dot step that you apply, but here we are doing or we are applying scalar dot step, which will do or which will see the update of the same as optimizer dot step. But since we have already clipped the gradient and unscaled the gradient values, so if my scaling is too much or too less, so that will be detected here. So that means if my scaling should be downwards, so that means if I have the inf value or nan value in this optimizer dot step stage where we are trying to update the values, so those updates will not happen for which the gradients have become nan or inf, but other gradients, other values will update the weights. So we do not want that, because we either we update all the weights or we do not update, okay, if there is any problem in the gradient scaling. So in that case, this scalar will actually see whether we have the inf or nan available in this gradient, and if there is, it will actually skip the update automatically, and we need to update the scalar. So then we have to update the scalar based on whether we have skipped or not. Okay. And if we do not use scalar, it will just do the loss backward, loss computation, backward computation, and then clipping, and then the optimizer dot step. and obviously then we are just calculating how much memory, and then we are running the comparisons across the number of samples, batch size, sequence length of 128. We are applying the criterion as cross entropy loss here, and total number of steps that we are applying to run for is 8 steps. Okay, so now if we run this guy here, we can see that the method which is applying for AP32 the full precision, it took around 84.13 millisecond per step, and in the case of AMP float 16 we have 35 millisecond per step. So that means the throughput has increased here, and with the peak memory usage of 1500 to 1400 is reduced. The loss, you can see it's almost the same. Okay. So the speed up we got around 2.4 times, and the memory saving happened for 8.5, very less memory, but the batch size is also very low, as well as the model size, overall size is also low. So with real workloads we usually get 2 to 1.5 to 2.5 speed up with around 30 to 40% of memory saving. Okay, so then we will go towards the dynamic loss scaling visualization, where we try to vary the scale, right. So the concept that we just talked about, that if you have, let's say, 50 steps to compute, and it will just see the loss scale value, and if there is the scaling required, or let's say it needs to be reduced. So if you see here, step 1, S is the scale factor which was doing the scaling of loss is around 65,000. For that it was okay. So that means all the updates got fine. So that means the S value stays, and around 500 step I increase the step, so double per okay. Okay, so basically after 500 steps, let's say I have doubled the S value because my updates were fine. And that point of time we see that this is okay, and it doubles. After doubling we see that this 501 step it detected the inf value. As I said, if you detect the inf value, that means you need to reduce the scale. So basically you need to update the scale again, and this step, which will be basically the updation of the weights with the gradients, so those values will be skipped completely, and rescaling will happen of the scale value. Okay, so then again you will come back to the 65,000. So that is exactly the thing you are seeing here. So this is called the dynamic scaling. So essentially you can scale dynamically based on, so there is no fixed scaling value. Okay, so each time if it is okay, if there is update happening, each step you double. If not, if there is any inf or nan is detected, then we fall back. That means we reduce the scaling. Okay, so after the 300 steps, the final scale value is, let's say, 16,000. This is how you dynamically scale it. Okay. Okay, so the next method that we will learn is the gradient checkpointing, which is very important for your large language model training phase, where you want to optimize the memory only. Okay. So during the forward pass, the concept says that during the forward pass, every intermediate activation I showed you, and where are the activations getting stored, because you have the forward pass. After computing each layer, you have the outputs. Those are basically the activations you store, and those must be stored for the backward pass, because when you do the backward pass, you have to do the gradient computation. So for the chain rule, you need these activation values. And for transformer layer with L layers, activation memory scales as order of L into batch into sequence length. So now you can see the complexity. If you increase the layer number, if you increase the batch, as well as if you increase the sequence, your activation will grow. Okay. And checkpointing, what it does is that it does not store the activations, maybe always not, or maybe not for the all layers. So we can discard the intermediate activations and recompute them during the backward pass. So we do not store them. On the fly, when we do the backward pass, for which layer I am trying to get the gradients for. So basically in the chain rule we do the backward pass, and that time on the fly we compute the or we run the forward pass to compute those activations. So we do not store them. Okay. So we just use the activations for computing the loss, the final output and the loss, and once the computation happens, then we do the backward pass, and that point of time we again do the forward pass each layer by layer to see the activations, because we did not store it. So that is called the checkpointing. So checkpointing stores the activations for square root of, for let's say these many layers. Okay. So that means I do not store all the layers. Okay. So order of square root of L, that is the memory, and or almost around 33% extra computation we have to do, because for those layers we have to compute, right. So here is one such model that we are trying with. So the small transformer block that we have seen already, which has the demodeled 512 dimensional vector as the input in the multi-head attention, and you can see it is divided into 8 such heads, and 8 such heads has QKV dimension of 64 dimension, and then after the computation the layer normalization happens with a residual connection from the combination of the attention outputs, and then the feed forward neural network, which is basically running on this 512 with an expansion of 2048 linear values, and then again reducing it to the 512 matching outputs, which is going to the next layer after the layer normalization, and you have, let's say, 12 such layers. And then you have the transformer output, which is basically 512 dimension of vector, and then you have the layer normalization, and then finally you have this n equal to 10 class output. So this is your let's say language model that we have here. Vocabulary size is 8192, which is mapping these tokens into 512 sequence. Okay, so now the definition of this deep transformer model is here, where we have this 812 as the vocab size, we have the 256 as the sequence length. So sequence length is how many tokens it should process, and then the blocks, basically blocks are the small transformer block, which is based on the vector dimension of the input, and then the head, and then the dimension of the feed forward network, which is basically 2048. Okay, so now here this is the model, and in this model, while defining, you can see that use checkpoint is use checkpoint, and this checkpoint either true or false based on whether we want to activate this or not. So essentially, once we activate under the blocks for which I have, so again you remember the module list, right. So it will create 12 such layers, because I have number of layers as 12 such layers of transformer blocks. Okay, then we have the forward function. So we are running the forward pass with the inputs, the positions that we have, then the embedding computation, and then the blocks. So here we have, if the self checkpoint is happening, okay, so checkpoint recomputes the block during the backward. In the forward, we do not store the activation for this block. So which block? That is defined in the block. Obviously this blocks is the blocks that we have defined in the module list. Okay, so for each multi-head attention, I am not storing the activations, because the most number of activations are stored here, because here this blowing up happening from 512 to 2048, which is, I mean, the number of activations stored here is very high. Okay, so now in this case we are returning the head. Okay, so now we are measuring the training step, and basically we are with the optimizer Adam W, Adam weight decay, and then the cross entropy loss, we are creating this training pipeline. Okay. Now with this number of layers, batch size of 8 and sequence length of 128, we measure the time and the memory that is required for the standard model, which stores all the activations, and the checkpointing model, which recomputes. And you can see that the memory that is required around 1500 MB, and for checkpointing we need around 1100 MB, and you can see that the time is increased here, because you invest more time while doing the backward pass for the forward computing. So, for this very simple model, we have saved the memory by 30%, around 30% is saved with the compute overhead of plus around 27%. Okay. You can scale the batch now. Now you can do the optimization and study of the impact of batch size. Obviously, now you cannot increase the layers or decrease the layers if your model is fixed, but you can increase the batch size from 2, 4, 8, 16 and 32, and if you just do the experiment, you see the batch size. So here is the graph and actual sizes are showing here. So for batch size of 2, you are storing around or using around 451 MB, and for checkpointing with 32 batch size, you are taking around 460 MB, which is almost same around with your batch size of 2 or for that matter 2, 4. You are supporting batch size of 32. Okay. For batch size of 32 with standard model or without checkpointing, you need around 1000 MB, which is almost more than double, right? Obviously, you have a bit increased time, but that is okay if you have saved almost around 2 times memory, or 50% memory has been saved by using this checkpointing. So checkpointing is very important. If you want to save the memory, you can invest some time in the compute, which may not be very high if you go for larger batch size usually, and you save the memory at the same point of time. Okay. So in the next class, we will see other techniques for the LLM training and optimization, and also overall computation plus memory optimization techniques for large language models. Thank you.